So let's get started and welcome everybody to Geospatial Forum at our usual time. And I'm very happy to welcome Michael Starek. Some of you know him already because he worked here at NC State for a couple of years. And his bachelor degree in environmental science with minor in geology and math from Texas A&M University, Corpus Christi, and he got master's degree there also in computer science, so really interdisciplinary. And then his PhD is in civil engineering from University of Florida, and he was there when NCAL, the lidar center, was there, so he was really working with people there. And currently he is associate professor at Texas A&M University, Corpus Christi, and he is also a director of MANTIS, that's Measurement Analytics Lab there, and he is leading a program where they do a lot of work with UAS and with surveying. So we have a great opportunity now to learn more about what's happening there and what are the great technologies that they are using and developing in South Texas. Yeah, so
Great.
I will leave it to.
All right, well, yeah, thank you very much. Glad I made it. It was very stressful 2 days of waiting in the airport. Got the last absolute seat to even get here today. Supposed to be here last night. So anyway, hopefully I'll stay awake through the whole thing. Was up very early, but it's great to be back. I was here for a postdoc for a couple years here and working with Dr. Matasova, and really nice to be back in Wolfpack country. So again, yeah, it's Mike Starek. I'm associate professor very recently. Geospatial Systems Engineering is the name of our program. It's a name change that we recently did. And today I'm just going to show some examples of, I know y'all do a lot of really neat UAS work. Some of the stuff we're doing with UAS related to South Texas and more regional focus, and a little bit of some examples, some new stuff we're working on. Just very quickly, I'm affiliated with our programs with the Conrad Blucher Institute for Surveying and Science, which was dedicated in May 1987. Blucher family, they're a group of surveyors in South Texas, 1882 to 1954 basically. And so that institute that I'm a part of supports our academic programs. We have a bachelor's, a master's, and very recent we have now a PhD program called Geospatial Computing. And our institute's really well known for coastal environmental observations, so they set up, in fact, Dr. Gary Jeffers happened to coincidentally be here today, who is director of the Blucher Institute. He was given a surveying seminar. We didn't pre-plan it, so invited him over. But he was, they're well known for setting up the Texas Coastal Observation Network, TCONS, which is a set of tidal datams across the state. So we do a lot of coastal resiliency, emergency response, those kind of things. And this is actually a picture of, I believe, Conrad Blucher's father. And this is what surveying's like, I guess, in Texas in the 1800s. Got to carry rifles. It's, I guess, hasn't changed. But and so anyway, I have a research lab at CBI, the Conrad Blucher Institute, called MANTIS, Measurement Analytics, and all the stuff I'm showing today is really our students, all their work. So they're the brains behind the operation. We have all kinds of students doing all kinds of different things, working from applications. I have a lot of surveying background, GIS, those kind of things. And in terms of MANTIS, just very quickly, where did the name come from? I showed this slide once in class about the mantis shrimp. If you are familiar, it's a pretty incredible multispectral vision system, though there's been some recent papers debating some of this. But they have incredible multispectral vision. We're a 3-band sensor. They're like a 12-band, or some even, depending, are even greater. So my students saw this and were like, oh, we got a car sells MANTIS. We couldn't think of anything, like we thought the name was cool, but what kind of acronym? So measurement analytics, the best we could come up with. But, the mantis shrimp, pretty impressive system. So what I want to talk about today is just small unmanned aircraft systems or UAS applications. Very strangely, this font appears not in this mode, so if anybody can translate this, let me know. But what I'll show is a little bit of examples. Yeah, so some kind of code, if you can solve it, you get a free drone. But so I'll talk a little bit on coastal mapping, photo bathymetry, example of that, and then a little bit on using UAS for estimating surf zone properties. And this is actually some work we did really early on when we first started. And then some examples of some of the agriculture work we do. We do a lot. We fly a lot in the summers down there with A&M AgriLife. And a little bit on UAS development, specifically a lidar system, what I would call a tactical grade UAS lidar system. And maybe if I have time, see how far I can get. Some examples of, we have one of the FAA test sites, one of the original test sites down there called Lone Star UAS, on some of the work on integrating UAS into the national airspace, so unmanned traffic management systems and how that's coming along. We'll see if we can get to it. So coastal, so what I want to talk about today are just some examples of, and there's a lot of work going on in this, but bathymetric surveying. So traditionally, right, we can have multi-beam, side-scan type sonar. Shallow waters, it's challenging when you're in boats. When you get to shallow waters, it can be a little bit more challenging. It's kind of like mowing the lawn. We have satellite techniques. We can do things like satellite-derived bathymetry and optical inversion type techniques, and we'll see an example of that in a minute. And then, of course, there's airborne lidar, bathymetric lidar that flies. It's a great technology. It can be very efficient, but it has challenges with turbidity. Those kind of things. There are now bathy lidar systems coming out for UAS, so the energies content in terms of depth penetration is challenging, but they're out there. Also traditional land surveying that we can come and survey right on the ground and near shore, different ways to survey the coastal zone, shallow water. But one nice thing is UAS provide one type of technique to image below water, so we call it photobathymetry. They've done it from aircraft too. The nice thing is consumer grade cameras, cheap, limited local scales. They can be flexible and efficient, just the things that we like. So there's different work going on in this with it. So again, I know most of y'all are familiar with this. So the way we do this generally when we're trying to map three-dimensionally is structure from motion or a structure from motion multi-view stereo aerial surveying. So basically we collect the imagery, we get a lot of overlap, and then we'll map an area and we'll derive a nice densified 3D point cloud. So this can work sometimes nicely in the surf zone, sometimes not. We've seen it work really well when water's clear, and we've seen it work really bad when water's clear, depending on the software and a lot of different things. So just to break down, this is kind of my own breakdown of SFM / multi-view stereo in terms of what different software do, like Pix4D, Photoscan. They have all kind of different ways of going at it, but essentially you're trying to automate a bunch of different images, extract features using some kind of like scalar invariant feature transform or some technique to pull these features that don't change due to perspective or changes in illumination and angles, those kind of things. And then they try to correspond them, and then basically that's where the traditional photogrammetry comes in. It tries to kind of simultaneously reconstruct camera position here, 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 and here. It's position and orientation. And then when it does that, it's actually kind of already you're matching those features. You're getting what's called a sparse reconstruction, so you get 3D points on the ground, or what we would call a sparse point cloud. So when it corresponds that, it generates a sparse cloud. And then what happens is a big leap in it is they do this kind of multi-view stereo densification type technique. And there's different ways to do it. And basically what it does is it comes back through where it matches features. So maybe you have an image with 1,000 pixels, matches 50 of them. I mean, that's generally a lot more, but let's just say that. So you have now, 950 pixels left over. Then it tries to come through and fill it back in. So in theory, it can densify in every pixel. If you had a 1-inch pixel, it could fill in every 1 inch, in theory. So it's this kind of workflow. They each go about it, but what happens is you get out this dense 3D point cloud, then we can use that to make a surface model, and then we can take that and try to ortho-rectify our images and mosaic them and those kind of things. So what we see is just working with them. Some of the software are sort of black box in nature. They're doing certain things. They can, again, terrain is a big influence on how these things work. So what's interesting about this to me as a surveying technology is like a LiDAR scanner, I kind of get an idea what it's doing. With SFM, I can go with Pix4D or Photoscan, run the same data and see quite different point cloud fidelity sometimes. So it's a pretty interesting problem. So what happens is that gets worse when you get in the surf zone or shallow water. So one of the biggest things is water is dynamic. This is photogrammetry. When things move around, it doesn't know they move around. So that's false parallax. That's already a big issue. That's one advantage of a laser is it shoots, it hits, it comes back. So that kind of causes issues. Probably the biggest thing to get specular reflection in Glint. So we'll see a lot depending on the software. It'll match Glint. You're flying over, coming back, flying over. You get issues like that. Sand ripples, low texture. Refraction is a problem, so you have to adjust for that. And there's been a lot of research and papers out on handling that and different things. And of course, it's optical, so poor water clarity. There's not much we can do about that to get around it. So that's always a challenge. So very early on, when we got a COA certificate of authorization to actually fly our campus. We have a naval base here, and this was back in 2013, and we went through like a 7-month process to get it for an EB. So we were using the drone to do a lot of facility surveying, and our students actually do that. And we fly it. We had a pilot on site, all the regulations, but all those products, surveying products, would go to facility surveying. We're actually student-run operation, our undergrads. We usually have one grad student, kind of what we'd call a campus survey, and to this day we still have it. But we also have a restored beach here that was restored. We monitor it with traditional methods at Conrad Blucher Institute, so of course we were interested in using the UAV to do it. But we had interest, one of my students, in bathymetry. He worked with actually a surveying company called Naismith, and they actually surveyed the beach. So what we did, we started looking at 2 flights that we did as an experiment to look at shallow water bathymetry. So this is very early on. We were first really getting into SFM and those kind of things. And so I'll show an example of it at 90-meter altitude. Then October, a windier flight of about 116-meter altitude, and a little bit different ground simple distance between them. So our platform was the EB originally. So we started working with that in 2013. We now have an EB Plus and many other platforms. But in the example I'm going to show, really the main thing here is, of course, we had a non-RTK GPS, so it's not accurate geopositioning. But the main thing is we just had a standard RGB 16 megapixel camera, so it's nothing fancy. It's the original sensor it came with. It's JPEG smooth. When you get outputs, it doesn't measure raw signal. So, however, we got pretty good results we'll see from it. This is what happens when you let undergrads, though, operate a very intelligent system. They figure out how to have it hit trees and then laugh about it and send me pictures. But at the time, this platform was $27,000, so I didn't think it was very funny. But anyway, that's my one joke. So, but here's an example of our beach survey setup. So this is the beach, routinely monitored. It's pretty interesting how they restored this. So it's actual beach that got restored. It was there naturally and disappeared from certain factors, and we brought it back. But one of the things we were looking at was testing different control targets underwater in coloration. But these are actually RTK transects here that are running. So we had surveys that we did where we had ground truth from it. So here's an example, and again, it can vary. Our August flight data looked great underwater. Our October flight, I can look at the images and see the ball and look fine, but yet, at least at the time, and the algorithms built, and we're using Pix4D for these examples, had issues. But this would be a typical noisy point cloud over water. So you can see very correlated points that'll jump way up or way down, and you'll see good returns or benthic returns. It can be highly noisy. It can work great sometimes, and it can work really bad when you're looking at the imagery and saying, why is it not working well? So what we observed, at least in these experiments, is matching successful only in areas with visible texture, for example, seagrass, so that's common. Texture is very important for this. Image scales where you can blow up, so it kind of smooths it, and sometimes that helps, especially on crops where things are moving around or texture is real similar. Could smooth it out, but that didn't improve results. But this is just an example of what we might see. So what we did, I had a student start to look at this problem. So here's an unfiltered SFM cloud, a bad one over that water, even though it was fairly clear and we should have got measurements. We can strip it away. So he came up with a method to try to denoise the signal and pull out what we call good returns. But we still see issues. We still see huge gaps in data here. And again, it's just shallow. It's less than 2 meters, a meter really. Should be able to work, but we're having problems for whatever reason with the surface dynamics, etc. So some other things you can do is set up like match constraints. That means you force it to work with more images that overlap. Generally you have a less noisy point because you have more observables, so it constrains the solution. So that works pretty good actually to remove noisy points, but you can see we start to lose density quite a bit. In Photoscan and other software, they have different ways to try to go about and remove noisy things or not. They all have their pros and cons. But the issue was, regardless, at least in this case, we weren't getting any returns anywhere, and we thought, well, this should be doable. So we looked at a common technique used, which some might be familiar, is optical inversion. So it's a classic remote sensing technique where you look across different bands. Done a lot now, actually, with satellites, and really usually in very clear water. It's not the most accurate method, but basically you're looking at, near infrared gets very attenuated by water unless there's a lot of sediment. Blue to green tends to penetrate more. So you look at how these things attenuate. The simplest case is by the way, I'm colorblind, so it's hard for me to see this laser, so I'll just use the pointer here. But the simplest case is you just kind of do a logarithmic linear fit, and generally this is done with a hyperspectral sensor, so we're talking here 3 bands, red, green, and blue. So we went through, and what you do basically is you need some kind of training data. So in our case, we had RTK points. What we do now is we take the good SFM points and self-calibrate it. But the downside of this method is, again, that you have to have some truth to calibrate these models. And then some people take it, and researchers will take this and, of course, go for a more fancier, some type of machine learning method or other approach that handles variation a little bit better. But anyhow, we wanted to look at this problem. So what we do is we'll just take the imagery. Again, it's a 3-band RGB sensor. We'll use the red channel to segment the water out from the land because we need the water. Then we will normalize the bands to try to remove any effects from brightness or glint off the surface to try to kind of normalize that to some degree. And then what happens is once we have that, we simply take a subset of RTK points, calibrate the model, and we can fill in our depths. Surprisingly, we were getting pretty good residuals around about 8.2 centimeters with this fit. So just comparing it, what we did is we took it, as an example, we took the denoised SFM point cloud. So this is what we call our good structure for motion bathymetry. And we had targets underwater, so refraction is already kind of compensated, versus our optical inversion approach. So interestingly, SFM was biased below the true, what we'd call the quote-unquote true surface from our RTK survey. And then optical inversion was slightly biased above, but we had a much smaller mean error. It makes sense to some degree because we are cheating in that we're using training data to kind of calibrate this model. So there's been a lot of work and ways to, again, self-calibrate these things to remove ground truth from it. So the way, again, that we can do it is you can take the SFM and take that and then combine them. And there's even other approaches where it's purely optical modeling that people have worked on if you have a higher band sensor. But this, again, is just an RGB example. But what we can do is, pretty interestingly, we're able to fuse. So we'll take the SFM denoise points, especially for the exposed topography, and fuse it with the optical inversion depth. And then we can reconstruct a fairly accurate topobathymetric model from it. And again, at least as a surveyor, bathymetry is always challenging in the surf zone. So it's an area we have an interest in. There's a lot of neat work going on in this. And here in a little bit I'll mention one other technique. So we carried this on at another student. So this is a project where we were actually looking at submerged pipeline detection with a certain bathymetric lidar system for old oil rigs or oil wells in a bay. But we wanted to look at UAS and just see some of the things we could do. So what we looked at here was a technique called image preconditioning. So in this case, we flew a near-infrared, red and green sensor that records raw signal, so it's not smooth. And we're looking at here in Corpus Christi Basin. This is in South Texas, and so we have wetlands and other things, mangroves, you can see in the background here. And we're keeping all of our point clouds on ellipsoid height. So what we want to do here was basically take the imagery and just play tricks with it, try to remove glint, try to work with single band, base glint removed, run it through the SFM and just see what happens. And ultimately what we're trying to do is, can we get deeper with certain techniques and map the bottom better than other ways of taking, for example, the standard RGB imagery through it. So as an example, we looked at different glint correction methods, because that kind of noised our signal a good amount. So there are two common ones from the remote sensing world, Headley et al. And Lizanga et al., and they all require near-infrared bands. So what we do is take our imagery through, run through these glint correction methods and basically pre-process the imagery, and then go back and feed it through the structure for motion workflow and see what happens. And here's an example of that workflow. And then also what we did is we took the images and we'd split them into red, green, in this case near-infrared. It makes sense that green, in theory, because it's less attenuated if the water's clear enough, should work out better. We split it. We splint the glint correction methods, and then we take our original RGB imagery and we just run it through, in this case Pix4D, through a processing workflow, take it through, and ultimately what we're doing is we're going to look at statistics of just our, in this case, their ellipsoid heights. We didn't want to use any control targets. We wanted to feed everything the same exact data and just look at how does these different preconditioning methods affect a structure for motion point cloud, essentially. And does it make sense? So here's an example. Here's our original imagery. So this is the land, this is the water, so we see gaps. Here's the Headley et al. Glint correction removal approach, so we fill in some. Surprisingly, for whatever reason, the Lizanga et al. Algorithm, well, there are some reasons behind why it works better, but we're able to actually, with glint removal, fill in more returns from the bottom. And again, same exact data, it's just different ways of preconditioning the imagery. So that shows you the weird way of SFM multi-view stereo surveying or mapping. It's interesting like that. This is pretty neat. Here's a single band. So here's a near-infrared, red and green. So near-infrared, again, should be strongly absorbed in water, which we see happen, except this is a very turbid area. There's seagrass, so we do actually get reflections from the surface that we can get measurements from. And then here's the red, and then here's the green. And so just looking at the statistics, compared to our original multi-band image, this is just looking at point density, we had a reduction of about 20% with the near-infrared, which we would expect because of attenuation. The single band red did a little better. The green, we got an increase in point density, not too much above the red, but what's really interesting is if you take the mean ellipsoid height between red, near-infrared, or green, we're almost 2 meters down deeper on the green on average, which shows that even though the point density is similar between the bands, the green, because of light penetration, which we expect, I mean, it makes sense physically, we actually got a point cloud that's resolving more from the benthic layer. So it's pretty interesting work. It's just examples of different ways you can play around with these things when you're trying to work at bathymetric mapping. I didn't put a slide here, but if anybody's heard of fluid lensing, is a technique that's pretty interesting that NASA developed that's going at this from a different perspective. This kind of relates to it. So this is particle image velocimetry. So this is just an example. Here I'll show here just this summer we had a NSF research experience for undergrads that came, and it was computing on U.S. technology. And we had a couple students come, one from Boston and Haley, she's local to Corpus. And so all students worked on different things. So this one we just wanted to try basically doing a technique. PIV is used a lot for hydrodynamics, fluid dynamics, and the FRF facility does a lot on the beach with imaging, from setting up static cameras and looking at these properties. So basically the idea is you take a drone, you use the video camera, so we're not doing SFM here, we're hovering high frame rate video and just basically trying to record the wave field as it's coming in. The idea is we want to estimate surf zone properties. So what they worked with is there's an open source tool called Python PIV. This is our pier here locally. This is Bob Hall Pier in Corpus Christi. And so they went out, we ran experiments. So hovering up above, we take high frame rate video, we image. And then what we use is this static features, including targets and the pier, to try to correct for image stabilization. So as things are moving around, what we want to do is remove that to try to stabilize the image, because basically how this works is it's trying to track particles moving through each pixel. If you know the pixel size and you know the frame rate, you can compute velocity. And then what we can do is if we do that, we can convert these particle velocities to actual wave velocities. And then there's things like linear wave theory from coastal engineering that basically allows you to relate those velocities to actual depth and other things. You get wave heights. And again, it's very hard to measure this stuff. I mean, I have to go install a buoy. It's a rough environment, or some kind of sensor down there. Maybe I sit on the beach and try to ping it with a scanner, but it's not an easy place to measure things. So this is just kind of a neat test case of what we could do with it. So they ran this method through it and took it. And then here's an example. So we had some crazy errors here where movement on the pier and other things were causing issues. But in our target zone, this is our second sandbar where most of the breaking waves, they're able to fairly realistically estimate velocity fields. They ran some tests where they were trying to, field validate the data. So we didn't really have really good ground truth in this case, but it was actually pretty successful. So, a different approach. And then what a lot of people are doing now is taking these velocity fields like this and again applying different types of linear and nonlinear wave theory in the shallow zone and trying to invert bathymetry out of it. So a lot of work on totally different approach between that was SFM. This is PIV. And then again, NASA fluid lensing, which is pretty fascinating. Apparently, it's got to have really ideal clear water conditions. But that technique will actually take wave properties and kind of like an image preconditioning method, it'll sift through and look for really high frame rate video and try to sift out certain wave properties where it basically removes refraction and then they can pass it back through. But anyway, there's a cool video about it if you get a chance to, if you haven't seen it, it's pretty neat. So that's a little bit on some of the coastal work we're working. So now I'm going to move on to agriculture, which we do a lot of work in, being South Texas. So this is work with, real quick, with Texas A&M AgriLife Research, who we work with quite a lot. And of course, Texas is a big agricultural state like North Carolina. So this example here is strictly going to be on monitoring corn growth or maize height. So some of y'all are probably familiar, some not, but crop height's actually, when working with crop geneticists and crop scientists, one of their main metrics that they measure performance. So they're looking at different varieties and how they perform. It's really growth. And so how they traditionally do it is a field measurement. They generally do it on a per plot basis. The example here is they went 5 times during the growing season, but we're looking at what they call flag leaf height. They'll basically take a ruler. They usually do 2 plots, 2-row plots, and they'll go out and measure maybe 3 measurements per those 2 rows, take the average, and then report it. So in this study, we had 5 of those measurements throughout the season. And then we also had a lodging event. So lodging is where the plants will fall over. And so we had some folks go out and estimate and measure lodging. And so what I'll show is an example of measuring heights and then using that to automate lodging detection, essentially, which is an important measurement to get from it. So we've been flying out there. Every summer we have students and groups. So this is 102 degree Fahrenheit, fun South Texas summer, collecting a lot of data. There's our control targets. Always some love it, some don't. But we generally are flying weekly to bi-weekly. This will be just height measurements, but we fly multispectral, all kinds of stuff going on out there. So this specifically is corn. We do a lot of work in sorghum, and there's other folks going on. But we're always working with agriculturists in this. So in this example, what's interesting about it is we had 3 different platforms, essentially, different cameras from a fisheye lens to a Phantom, the original Phantom 4, not the Pro, which tends to be somewhat better for photogrammetry. But we had 26 flights over the summer growing season, so weekly to biweekly, a lot of data. So it makes for an interesting study of just how accurately can we measure height and monitor it. So here's our control network. The main thing to mention here is we had an upper trial and a lower trial. So I'm just going to show mainly examples from here, but these are basically just different varieties of commercial or genetic hybrids that they're experimenting with, and they plot them differently in different row designs. And again, they rely on that height metric to really study how things work or which one's performing better than others through it. So we run our typical, we set up for this whole area, we'll set up a big control network along this whole place for all of our flights. Over the years, we've learned a lot about things to do and not do with this. For one, they get really mad when they hit it with their tractors and things, so that's bad. They don't like that. We also have to resurvey these in quite a bit often. We used to see a lot of biases between flights that we'd have to remove, and because of compaction and other things that move around, so we got to resurvey in our control network. We've learned a lot over the years on getting better at getting it, making it more efficient, I guess you could say. So our standard processing workflow is again, we're going through structure for motion, but in this case, we're generally flying an near-infrared sensor of some kind, because ultimately there are a lot of times we're looking for spectral information or NDVI, but generally we'll get 3D point cloud, we'll take a surface model, we'll usually get what we call reflectance maps, and then these go into spectral information or structural. So we're really going to look at structure here. And in some work we combine both. But this study was really just strictly structural. And it's very simple for the GIS folks and familiars. We can take the data, we'll fly before growth, so when it's exposed, and we'll make a bare FDM. And then we'll go and just start monitoring the crops weekly, bi-weekly, and we'll basically generate a point cloud, make a surface model, difference it from the bare FDM, and then we get a series of canopy height models. So in this case, 4 centimeters. So the nice thing is we're getting this, every 2 days or every 3 days, 4 days, a week, which is incredible information for them. Simple, but we can do a lot of neat stuff with it. So one thing though is what they're interested in is measurements by plot, because they plan them by plot. So they don't. Sometimes there's an interest in per plant height. We can do that, right? I mean, we have the resolution, but they're really interested in an average measure for these 2 plots as an example. So, and they really like the ground truth. So what we had to do is we came up with a method to basically pull heights and average them per plot using the surface models. And it's just called a centerline height calculation. We can grow different centerline widths along these plot ridge lines. And then what we can do is take those and we can look at different percentile statistics and try to determine which metric, what width, what percentile works best for their data. And so that's what this study was about here, actually, was strictly for corn. What we'll see is corn works, some things work good for corn, some widths and percentile heights work better for cotton, etc. So what we do is we take these metrics and we would do different, look at different, basically try to tune it. And we had ground truth, I mentioned, they went out 5 different times through the season. That's our target. And so what we do is just tune through the 50th to 99th percentile height, basically looking at the digital surface model elevations or heights, the canopy height models, and just getting percentile heights between them. 99th will be a higher height than 50th, etc. And then we tune it for different polygon widths. And then we also looked at what about just taking the point cloud based surface model, right? Surface model using some spatial interpolation or smooth. We also wanted to look at resolution because that has an impact on flying. If we don't need to fly at 4 centimeters, we can fly higher. It's more efficient. Everybody knows the issues with endurance and those kind of things. But as an example, this plot's just showing different percentile heights for the 3 platforms, and this is days after planning. So this is a 15 centimeter polygon width. It's a pretty interesting plot. I'm not going to get into too many details, but the interesting thing is here you see this drop off in height, which they see a lot as crops start to get towards the end of their maturity. They start to dry out and actually lose height. The other interesting thing is the EB was at a much higher altitude. So what we're seeing here is we don't see as drastic this sigmoid growth function. We see the EB kind of very flat, and that's a resolution effect of the sensor in that case. Surprisingly, the Solo and the DJI are fairly similar, though they peak at different dates, and the EB peaked much sooner. So anyway, this is differences between the platforms. But in this specific case, I'm really concerned with what's my best way to estimate height. So as an example, here's just the different percentile heights, and they start to increase through it. So that's what we're looking at. So this is a lot of information in this plot. I think it's very colorful. But what we're looking at is centerline width, base percentile height. This is for the lower portion of the field, and this is relative to the ground truth data. So this mean absolute error. So basically down in this color is better between them. And so we just ran through a series of estimates. And then when we can take that, what we found out is in this case, between the upper and lower is the 25 centimeter width at that growth stage with the 99th percentile. 99th percentile is pretty common because we're measuring flag leaf. It tends to work pretty well. But we found that to be our winner in terms of the best metric way to estimate height for their needs. We had an R-square of about 0.92, so very good. So we also looked at resolution. So this is just real quick. We can see the 4 centimeters, 8 centimeters, 12 centimeters. So the error doesn't drop off that much, surprisingly. What happens is, I didn't show it, but after 12, once you get to 15, it really drops off. So in theory, we could have flown higher, much higher, gotten this much more efficient in terms of getting the same information. But what we did then is, that's one thing about validating those a way to estimate height that works well for their needs. But we had a specific need and what we were trying to do. So what we did is, with that method, we wanted to look at a way to automate crop lodging estimation. So that season, we just happened to have a high wind event that caused a lot of lodging. Last year, we didn't have a lodging event. Nobody likes to go measure lodging, actually. It was really hard to convince AgriLife to go out there and do the measurements. But again, if you're not familiar with lodging, lodging is displacement of stems or roots from their vertical and proper placement. So here's an aerial image of it, and then here's an example in the 3D cloud. And you know, there's very tricky between, is it lodged or not? Sometimes they'll recover, and sometimes they won't. So why do we care about lodging? Major destructive factors to degrade grain quality, reduced yield, delayed harvest, increased drying costs. So if they don't recover, you can imagine big storms, hurricanes, there's a lot of loss, insurance claims, those kind of things. It's a tedious metric to estimate. So we looked at this problem a bit and came up with a way to do it. What we do is we use our centerline heights. It's a pretty simple method, but we break it up now into individual grid cells along the rows. And basically what we're looking at are these thresholds between our percentile heights, 90th and 99. And this is just based on the empirical data, so we had to have some ground truth to tune it. I won't go into too many details here, but these two measures here are empirically derived. So for that time, the lodging event and the ground truth we had, we're able to come up with basically a threshold to say lodge or not lodge. And what that allows us to do is over an entire field. So here's an example. Red is lodging grid cell, I believe that's red. Green, I guess, is non-lodging. Oh, is it really? Oh my gosh. I've gotten worse. But ultimately what we can do is take it, and what we can do with that is, if we have the seeding rate, which we can get from them, or we have a way to estimate number of plants, we can compute basically a lodging rate per a plot, which is what they're interested in. They want to know genetic performance per a plot. So taking that with those estimates, taking the seeding rates and applying it across these different plots, we can then estimate lodging rates, high lodging rates, low lodging rates. And then, of course, the folks that study this have an interest in their performance and resistance to lodging and those kind of things. An example very simply built just off of one thing, a point cloud, a surface model, and height metrics. Obviously, there's a lot more we can do with these types of data and multispectral examples. So, just some examples of some of the things we work with, but now I'll talk a little bit about U.S. development that we're working on. And so I think this is pretty interesting. So there's a lot of work in U.S. lidar systems, like the Velodyne sensors, the lower cost ones. Somehow our engineering department got lucky and came across some funds to get a Regal VUX LR, which is a VUX long range. So this is what I would say is about as equivalent a sensor as you put on traditional airborne lidar in terms of performance specs. It's not cheap. It's got about 1,350 meter range, about 16% reflectivity at that range, multi-echo detection. So Regal's very well known for their online waveform multi-detection processing. It's about 7.7 pounds, so it's not light, but it's still fairly light, small enough to put on FAA small UAS. And so this is the sensor. We work with Phoenix Aerial Systems to basically integrate this sensor onto this platform called a Pulse Aeros Vapor 55. The biggest user of this platform, besides the military, is Sharkwatch in Australia, actually. They use it quite a lot for flying the coast. It's a serious platform. Its gross weight with payload is literally just below 55 pounds. I don't want to measure it. I trust them. So if y'all know the FAA, that's the magic number, but that means payload plus platform plus everything on there needs to be just below 55 pounds. Its max endurance about 60 minutes, hover endurance 45. When we fly this for LiDAR scans, we typically do about 30 minutes. Interestingly enough, we originally had a different IMU on it called a Latif Micro IMU. It's a MEMS IMU. It was more expensive than this one and was recommended to us because it's a little bit lighter weight, not much. Oops. Something happened. Well, anyway, so that IMU that we originally had So that's a single rotary platform. So when we were looking at the IMU measurements, its position, so its angular orientation, we saw a vibrational frequency issue or an error in it. It happened to be 20 hertz, which happens to be right at rotational vibration frequencies of that platform. So we had to replace the IMU to get good data from it. And we just did a replacement. So the example I'm going to show is with our new IMU that we took out called a KVH1750, which is a fiber optic IMU, which are generally better. They're both what we would call tactical grade IMUs, which means they can basically static align. They can sit and sense orientation where their air's low enough that they can do that and align themselves. So they're both good IMUs. But anyway, the interesting part about it was that was the one they recommended. And we worked with the integration on it, but it's actually turned out to be a lot of integration on our end with this system, a lot more than we were expecting, which is good. It's a good learning experience, but it's definitely a different type of flying with that platform. Excellent. Thank you. So again, so what I'm going to show here is what we had to do is when we install the IMU, we have to do what's called a bore site calibration and calibrate basically the sensor frame to the body frame and basically get the alignment of the lidar to the IMU so we can get better georeference data. So I should mention it also has a camera on it so we can basically texture the point cloud. It's a very nice sensor. So here's some of our students. They actually 3D printed a Wi-Fi antenna mount because there were some issues with the mounting, so they put that on there. The funny part about it is this is a very expensive system, but you fly it with an old Sony PlayStation joystick. They cut costs there apparently. It's called GCS flight control. It's very old flight control software. I guess the nice thing is it's simple. It's hard to mess up, but there's no, I want to fly at this height and get this much % overlap. There's nothing like that. We have to plan our flights and our grid lines and do it. It is autonomous, so we use this to do basically precision guidance. We launch it, we go, and then we can set it in auto flight. So it is autonomous, but you do take manual control, and I'll show that here in a minute. And so we'll see a video of how it flies. So in terms of our flight procedures, so even before we fly, it's a very rigorous safety inspection. I mean, this thing is serious and kill you. A lot of steps we go through. The batteries weigh 20 pounds, so it's electrical. They're coming out with a gas-powered one. But there's a lot just before we take off. But when we do fly, the basic idea is we'll first install everything, get the batteries, we'll check center of gravity. And then if you're familiar with LiDAR world, it's basically very much what we used to do or when I worked at NCOM with traditional airborne LiDAR systems. Very similar. We'll do a static alignment of the inertial measurement unit. We'll let it sit, and then we'll get an alignment complete. We're working with a Novatel or what's sensor, so we'll get that. And then what we do is we initiate auto takeoff, and then we'll take control. So auto takeoff, we'll take control with the joystick, and we'll do a heading check to make sure it aligns up on our flight control software. And so once we do that, then we have to do a lot of stuff to initialize the IMU to get good data. This took us a while to get at, and it's very important. We see this also especially with those Velodyne scanners. If you're doing mobile LiDAR, we have to do a lot of stuff. We see big issues in terms of how we align those IMUs. But anyway, what we'll do is after it aligns, we'll fly forward at about 10 seconds at 5 meters per second and basically ensure the alignment is good on the IMU. And then we do these things called figure eights or hippodromes. That's just to lock the alignment in and get what we call an INS solution good. So on board this system, it's actually taking the IMU and GPS data and trying to do a real-time post-process or trajectory solution in real time. So it's not real accurate, but it's something. And so what we do is we want to repeat this and post-process it later. So we have a very set protocol that we have to do. And then we'll fly that. We'll check and make sure our readings are good, our covariances, those kind of things. And we activate the scanner. And generally, it's just a very simple grid pattern because that's what our flight control software allows us at this point. And we just start scanning. And then when we get done, we cut it off. We repeat the hippodrome set. We fly 10 seconds. Again, we come and land. We let it sit for 5 to 10 minutes. And what happens is when we're doing our inertial processing, we do a forward solution, and then we repeat it in reverse. And that allows us to check errors and fix things because it's all about direct georeferencing here. And then we're done. And that's the flight. So as an example here, I'll show some data. This is just our example bore site calibration. We're flying back and forth over this airport hangar. This airport's called Bubba P. Wilson Airport. It's about as Texan as you can get. About 50 miles from campus. But you can see our figure eights before and after, etc. And so we'll actually look at some data here between it. But again, the main purpose of this flight was to calibrate that IMU into bore site calibration is what we call that. So here's a video of it taking off. LiDAR away. And where we live down in South Texas, it's one of the windiest places in the United States. We have an average southeast wind of 17 miles per hour. So this thing, we flew it in 30 mile per hour winds. It was extremely stable. Incredibly windy place.
Now we'll do a heading check.
So now it's hovering. We're still manually controlling it with the heading check to make sure it's locked in. And then we'll set it off and start flying.
LiDAR away.
All right. And so what's kind of neat about it is I mentioned that we have Wi-Fi transmission. It does an onboard direct georeferencing solution. So what's kind of cool about this system, which is neat, is we can actually get a real-time cloud. So this is actually the flight showing a real-time streaming point cloud. Now, this is not a survey product I'm going to provide someone in terms of accuracy, but you know, in terms of maybe disaster response or those kind of things or structural damage, it's actually fairly useful for that. So we're going to come here. You can see the images being taken by the camera. You can start to see the hangar coming up. So again, we get a nice real-time transmitted cloud. Of course, we'll post-process that and try to get the best data we can. So we'll take a look at that here now. So there comes the hangar, which is kind of neat as it's scanning through it. And it's a circular scanner, so it's just wrapping around. One interesting thing about this scanner is it has a very, very high pulse rate. So you get what's called multiple turnaround or time around events. That's where one pulse is going out, another's coming back. The scanner gets confused, it doesn't know. So Regal has a proprietary way to kind of remove that. So here's an example without MTA removal. So it just looks like a big cone of data. Here's after MTA removal between it. So very critical thing. We actually just had an update because what happens is we were still seeing some noise here. So they fixed this with a firmware update. There was an issue. But right here what's happening is our scanner is rotating. It's actually hitting the tail boom of the craft. So we need to cut our scanner angle off a bit on it. So this is actually platform noise where it's hitting, it's rotating. So it's just scanning like this. Here's some birds. It's kind of neat, capturing that. And so what we did is we post-processed using you know, our best practices that we've developed with the system in terms of producing the data. To this point, we still have a lot of work to go with this system. And that's the thing. It's a great system, but it's honestly, I get stressed out, and that's where I'm getting my gray hairs because of the money of that thing going up in the air. But anyway, this is a 2006 FEMA Airborne LiDAR survey, a traditional. It's a 3-return system. This is the only one, the most recent one I could find for that area for whatever reason. And here's our survey. So these are ellipsoid heights. So I'm just going to compare some differences in the data between them. So here's 2006, 2018. So some of the stuff's changed, but a lot of it's the same. So here's intensities. We get to the standard kind of intensity measures. This system, again, can get up to 15 plus returns between them, so we'll take a look at that. This is probably the most interesting thing. So we had an average about 1 point per square meter. So you can see our very bizarre point density pattern because we were flying a bore site calibration back and forth and around. But the interesting thing is in overlap zones, very dense data. I mean, you don't need that, but 3,000 points per square meter. Pretty incredible if you want it. And we'll see an example of this in a minute. Here's the number return. So this is what's neat about this system, is on the edge we had a forested area, so it's hard to see here, but we're getting 7 plus returns. So very nice data in terms of if you're looking for canopy measurements, those kind of things. But the nice thing about this sensor, so we have a Velodyne, is the precision of this. If you compare the two, very precise relative to some of those Velodyne scanners. But again, the cost. I mean, you're looking at difference. That's what you're paying for. So as an example, here's the hangar from the Airborne LiDAR survey. And then here's an example with the textured point cloud from the camera. So you can see the level of detail between them. And then here's an example here of that. So very detailed, so you can imagine. So it looks really good, but unfortunately, I got another story to tell here. So here's the roof, looking at it, very nice. Here's the airborne transect. So this is what that looks like in the traditional LiDAR. Now, again, it's an older LiDAR system, but still, it gives you an example. So here's the UAS LiDAR post-processed, but let's zoom in a little bit to it. So zooming in between, we did 2 flights for this bore site calibration experiment. We flew, landed, and repeated exactly the same. We're seeing some offsets here. Now this is, I know what this is. We have to work on our calibration routine. That's for looking at an IMU bias. So there's ways to calibrate that. We need to work on that and get it improved, basically. But those are things we can fix. But this is an example of some of the issues that we work on and try to correct with it. But overall, in terms of fidelity of this measurement and the scanning capabilities and the range is pretty impressive. So we're pretty excited about the system. But you know, that platform honestly, it's a headache to fly. So we're actually looking at mounting that on a experimental gyrocopters. That's piloted craft because it's kind of a hybrid between a drone, piloted aircraft, but the rates are much cheaper. So we're working with a company down in South Texas to try to integrate that on that, and expands a lot of mapping operations that we can't do with small UAS right now, mainly because of regulations. So one other thing, I have a little bit of time. We have a NSF MRI grant to develop an integrated gas monitoring UAS. So it's working with a Penguin B UAV, which is out of Latvia. The main thing here that we're doing is, I'm a co-PI on this, is integrating this greenhouse gas analyzer. So it's methane, CO2, H2O. And then we'll have a camera on there just for mapping, but the real purpose is for this, for gas sensing. And then right now, basically what we're at is we're trying to install the flight controller. It's a Piccolo flight controller is what it's called, and we're trying to get that integrated. This has been, again, a process itself as well, getting it up and running. Hopefully we'll have it flying. It's been over a year, and we still haven't got it up in a year, minus test flights in Latvia, which I didn't get to go to. But anyway, a system we're working on to develop. And then I have a little bit of time. I think what I'll show here real quick is just, I know y'all had Hurricane Florence. We had Harvey last year. It was a pretty big, we got very fortunate, at least where I live and at our university. So I'll just show an example. So the Florence was a big rain. Harvey was both rain event and wind, but where we were, it was all about the wind. Massive winds, Cat 4, estimates of 3-4 hours of Cat 4 winds in places up north of us. So here it is coming in. Here's the track. Here's actually our campus right here. So it went to the north of us. So most of the coastal erosion really was fairly unimpressive until you got north on that northeast quadrant. This is called St. Joe's Island. It's basically undeveloped, private island. They had massive breaches through there. Down here we were fairly stable. But here's our campus to give you an idea again. So this is Corpus Christi Bay, Oso Bay. Had this hit us below, I mean, you can imagine the impacts. I don't think I'd be here right now probably still wouldn't be on campus. But where we were at, we had a max of Cat 1 wind gust at our camp, just barely. Basically it came through here where they recorded Cat 1, and then it was basically tropical storm. This is Corpus Christi in here. So we got very fortunate. But to give you an idea, Port Aransas is located just 16 miles northeast of our campus. They just got the southern edge of the eye wall, so this is the wind damage. They also took surge from the backside, so massive. And then Rockport, which is a lot on the news, maybe some of y'all saw this, took incredible amounts of wind. So you can see the gust here, 150, 140, etc. So what I'm going to do is just show an example of right here, just a 3D point cloud. We went part of a team. We've done a lot of erosion monitoring with structure from with the drones and that kind of stuff post-Harvey and seeing how things are recovering. We did have one breach locally, and we've been monitoring it. But this is work we did as part of a team with, it's called Geotechnical Extreme Events Reconnaissance. I'm sure there's NC State folks here. Mainly it's structural engineers. They chase storms all over the place, and they're basically looking at building code performance. So we went with the team as a volunteer network to image one neighborhood that got hit really bad in Rockport, called Salt Lake. And then, the structural data, the 3D point cloud data is used to help them estimate their measurements on the ground and go through it. So I just want to show real quick an example of, some of the impacts that happened there. So let's see. So just a standard 3D fly-through, but you can see here it's pretty incredible some of the damage from that wind that happened in this region. So you can see complete wipeouts in places. And what's amazing is the way, and again, what GER is about is why did this do well, why did this not do well. Texas has a lot of different building codes for hurricanes relative to, say, South Florida, which is very rigorous. Of course, UAS is a great way to capture that 3D structural information. We're just looking from the top, so the sides of things, but we can come, as we get through here, we'll start to see an area. Let's see. So we'll come across over here, but we can see, and you can see, of course, the issues on water that we always see, but you can see areas where completely taken out. They've recovered pretty well now, but incredible amounts of impact with it and with this data. And it's actually, this data is hosted, available, and there's a bunch of folks that went on the ground, and they have a University of Texas hosted, so all the data is actually out there and available. Not only the UAS data, but the field collected data and those type of things. Given the time, I think I'll stop there. And I appreciate it very much. Thank you again for having me here. And just really quick, this is actually our first, they had this back in our university back, it's RS-16. They're flying it back in 2010. They had a COA on Kennedy Ranch and King Ranch, which is one of the most isolated places in the country, is why they got it. So this is our very first UAS that was being flown on our campus. And it has a thermal imaging system, a UV sensor. The issue was to fly it, you had to hire a chase airplane to follow it. You need a real, it's not a small UAS, so it was very cost prohibitive. So that's basically not getting flown much or too much anymore. But anyway, thank you very much.
Thank you, Mike. I think we have time for a few questions. So please ask your questions. We have people here who are getting ready for flying or
Excellent.
are already flying. Okay, so Nick, what's first?
I wanted to ask you, so it looked like you use mostly off-the-shelf sensors. If you could design one, let's say for your bathymetric work, what does that look like? What wavelengths are you collecting? How many spectral bands?
Well, if I could do it, I would get a bathymetric lidar that's basically blue-green, so 532 nanometers, and pump the energy really, really high and hope there's no fish. And because if you get, I mean, it can do it with really high energy. You can pulse through pretty deep, and I've heard folks experimenting. But if I was to try the inversion approach, a hyperspectral sensor. I mean, there's a lot you can do with it. Now, there's a sensor called MIDAR, which comes from fluid lensing that NASA, a guy named Ved Giroff, is developing. That's a pretty interesting. It's really cool what they're doing, but it has to have very unique, at least right now, my understanding, very nice conditions and like coral reefs and things, and it works amazing there. But if I was to try to repeat that experiment, I mean, first would be a hyperspectral sensor to get more bands if I want to do optical inversion. But if I was to go at what's the best aerial method, I would say some kind of bathy lidar or a photon counting that's very sensitive. But if you can pump the energy up and you have a photon counting, in theory, it can get through pretty turbid water, but there's regulations, eye safety, those kind of things. Yeah, good question.
Okay.
I have an uncomfortable question. How much was this paper?
Yes, so first let me say I did not pay for that. How they got it, I had this funny story. I'm very glad we got it, but I got a phone call and said, do you want to get a UAV light from my Dean of Engineering or Associate Director of School of Engineering? And do you want to get a UAV lidar system? I said, sure. He goes, well, we have something like $400,000. You need to spend it in 2 hours. You need to get equipment. I said, what? Okay, so somehow they got a hold of heat funds, I think is what it's called. Somehow they got a hold of some funds. So I knew two companies at the time that were, this is a few years ago, because it's taken us a while to even get to this point. And the reason is because, well, I'm busy. It's not something I can send my students to do. So we rely on, real, field techs or folks that can come out and fly it. But the sensor itself is about $330,000 when you add the platform, all the software, everything together. I mean, the lidar sensor was around $100K at the time, but then you add the IMU and you add that. The platform's about $80K. I think they might have gone down a little bit in price, but everything together was around that. So some of that you could cut out, some of the software and those things, but it's an expensive system. But yeah, at the time it was kind of interesting. It was like, you got 2 hours, so I knew LiDAR USA and Phoenix Aerial Systems were both integrating LiDAR units on platforms. I went with Phoenix because of this platform stability. There's a one called a Rycopter, which I've heard good things. Everybody has pros and cons. This has issues too. In fact, we had to send a part back to get replaced for safety recently. But Rycopter is one that they're flying, that Regal, the maker of the sensor, flies. This platform, though, is very efficient. It can cover big areas. But, again, regulations. So, UAS LiDAR has a niche area in terms of what you can do with it right now, unless you're able to get beyond line of sight or those kind of, not myself. But that's a very good sensor. And again, if I didn't show it, but if I compare that with some of our other, we work a lot with lower cost Valadyne, all kinds of other sensors. I mean, you see the difference in the range, and it's a really nice sensor. And I like Regal, I like their sensors. But yeah, it's not cheap, but it was over $300,000 total with everything. So that's what it,
For the UAV, the small one. The small one, but for the UAV, it's like
right, so they have the new one out, which is the Vux, the Mini, the Vux Mini.
Yeah.
This one, the nice thing about this is it's very, so for example, I mentioned about wanting to do gyrocopter work with these folks that have basically they have an FAA approval for experimental gyrocopter to mount sensors on them. So that range is really beneficial to have with it. I don't know what the Mini Vux might have the same range, I'm not sure, but this is the longer range one, so which is nice. And of course, the thing is, it's going to be, outdated and definitely cheaper. But the Valadynes are great. I'm a huge fan of those because unless you really need something like that, and again, the costs are coming down. This was when I was in grad school, that was unheard of to say it was below $1 million. For a sensor, there was not a sensor you're mounting on a drone. There weren't Valadynes really being put out there. So, $5,000 LiDAR scanners was pie in the sky stuff at the time. So, of course, this is going to be, I'm sure they'll outdate it in another 6 months. But it's a very good scanner. So I look at, with that, a 5 to 10 year, well, I'd say we get good data for, honestly, for a lifespan of 10 years probably, in terms of data quality, unless there's some new thing that comes out that changes the game.
But you need to like put together the sensors and
Well,
that from yourself?
Well, that's the thing. It turned out to be a lot more integration than we had expected. I thought it was just, it's not. It's a lot of just getting our protocols down, our best practices, but that IMU issue, that was recommended to us. We had to go back and switch it out. That was what they said, no, you should get this one. And in fact, it had the worst one for that platform. It's kind of funny. So there's been a lot of work that we have to do on that end. But again, and then the other thing is we're so used to flying the smaller ones. We fly all kinds. I have some students that are just completely open source. We'll mount anything we can mount on them and fly, and we use Mission Planner. And then we have the EB for our more production workflow. But that's been a good learning experience for myself personally in terms of just flight operations, honestly. And the data is really pretty neat. So we're really just starting to tap into it.
Okay.
Yes?
You mentioned when you were doing the structure for motion that you had some black box issues trying to determine what was going on between Pix4D and Agisoft. Have you looked at using OpenDrawMap as another option for that?
Yeah, so I was talking to Vikas, right? Vashik. That's close. Vashik. Yeah, so we did one of my students did actually early on a study between Pix4D, Agisoft, and OpenDrawMap, and what he did is he went and flew all kinds of different terrain and then tried to feed everything the same and try to control everything the same. And at the time, so we aren't OpenDrawMap power users, but we could get okay orthos. Our point clouds are pretty bad, but this is 3 years ago. And he actually published a study. It was in GIM International. It's a trade magazine, but it's a pretty interesting paper on the differences between them. Well, I mean, so Photoscan did great at true 3D modeling, which is what it was originally, my understanding, designed for. It actually outperformed. We found Pix4D, in terms of if I want to say what's most accurate, Pix4D seemed to be at the time, but again, we weren't trying to tweak a lot of things. But OpenDrawMap was pretty impressive with what we were getting. We just, was just a case study. So in fact, I was talking to Vashik about trying to get, I heard it's improved quite a bit. So we definitely want to get more into that. And then we started with Pix4D because of the EB. We had a software called Post-Flight Terra, which is basically Pix4D at the time. And so we got very comfortable with it, but a lot of stuff we do now is photoscan. When we can't do stuff in Pix4D, we go to photoscan. We'll pretty much use whatever works. But yeah, no, we were impressed with what we could do at the time in OpenDrawMap, but definitely great to hear it's getting much better. So.
Yeah, they've done a complete changeover in some of their background libraries in the past 6 months. So
Yeah, definitely.
Okay.
Thank you.
More questions?
I have like 7, but I'm going to pass.
Okay, thank you.
All right, thank you again. Thanks for having me. I really appreciate it.